Hello and welcome to The Sleepy Scientist. Before we begin, I'd love to know, where in the world are you listening from tonight? Whether this finds you under blankets, on a late evening walk, somewhere on a long quiet drive, or simply hiding from the chaos with a cup of tea and a scientifically respectable level of tiredness, it is always lovely to know where these videos are reaching. If you enjoy this kind of calm, curious journey through the universe, please subscribe to the channel and give the video a like if you find yourself enjoying it. And to everyone who already subscribes and keeps returning to spend these strange and sleepy hours here, thank you. It genuinely means a great deal that so many people choose to spend their listening time on topics that include such glamorous material as quantum fields, vacuum states, and the possibility that what looks like nothing may in fact be one of the busiest things in the universe. Tonight's question begins with a surprisingly ordinary thought. Empty space seems like it should be the simplest thing imaginable. No stars, no planets, no dust, no air, no objects at all. Just absence. Just a clean, silent gap where absolutely nothing is going on. A sort of cosmic blank page. Very tidy, very convenient, almost suspiciously convenient. Because the deeper physics goes, the less that idea survives intact. What looks empty turns out not to be truly empty in the way common sense expects. The modern picture is far stranger and far more interesting. According to quantum physics, even the quietest regions of space are not mere gaps in the universe. They are structured, active, and filled with fields that never fully switch off. Which leads to the wonderfully unsettling question at the centre of this video. If empty space is not really empty, then what exactly is there instead? To most human senses, emptiness seems very easy to understand. A room feels empty when nobody is in it. A box feels empty when nothing rattles around inside. A patch of sky looks empty when no bird crosses it, no cloud drifts through it, and no aircraft leaves a white line behind. In ordinary life, the word usually means the absence of familiar things. No objects, no clutter, no movement, no obvious activity, nothing to notice, and therefore perhaps nothing there. That everyday idea is perfectly sensible. It works beautifully for cupboards, bowls, wallets after online shopping, and train carriages at inconvenient hours. But physics is not usually satisfied with what feels sensible from the human point of view. Physics has a habit of taking ordinary words and placing them under an extremely bright lamp until their edges begin to blur. Empty is one of those words, because once the question becomes more precise, the idea of emptiness starts to slip away. Is a place empty if it contains no chairs, no planets, and no dust, but is still filled with air? Most people would probably say no. A sealed room full of air is not empty. But what if the air is pumped out? What if all the gas is removed until the pressure is extraordinarily low? A laboratory vacuum chamber can be made so sparse that only a tiny number of particles remain. Is that empty? Closer perhaps, but not yet, because light can still pass through it. Electromagnetic fields can still exist within it, and gravity still acts across it. Even a region with almost no matter in it is already doing more than the ordinary word empty suggests. Then the question grows sharper still. Suppose every atom is removed. Suppose all visible matter is gone. No gas, no dust, no drifting molecules, no lonely grain of anything at all. To common sense, that sounds like the finish line. That sounds like true emptiness. And yet modern physics says not quite. Or, more accurately, not even close in the deepest sense. This is where the conversation becomes strange, though not in a mystical way. The claim is not that empty space is secretly full of invisible pebbles, hidden smoke, ghostly fluff, or some cosmic attic junk that nobody noticed until the 20th century. It is not a trick of wording. It is not the scientific equivalent of saying a biscuit tin is empty apart from the biscuits. The point is subtler than that. When quantum physics describes empty space, it is not talking about a secret pile of ordinary stuff. It is talking about the fact that even in the absence of ordinary matter, the fabric described by modern physics is not a blank nothingness. That difference matters enormously, because the whole title depends on it. Saying that empty space is full does not mean space is crowded in the everyday sense. It means that what physics calls the vacuum is not the same thing as simple non-existence. The vacuum is not just nothing, it is a physical state, and that idea only makes sense once ordinary intuition is gently taken apart and rebuilt. It is worth pausing here, because this question has been around for far longer than particle accelerators, orbiting telescopes, or laboratories full of expensive lasers and people with extremely determined eyebrows. Long before quantum theory arrived, ancient thinkers were already arguing about whether emptiness could exist at all. Democritus, the ancient Greek philosopher associated with early atomism, imagined a universe built from atoms moving through void. In that picture, empty space had to be real, because without void there would be nowhere for atoms to move. Motion would become impossible. The universe would be a kind of solid traffic jam with no room for anything to happen. So for Democritus, emptiness was not a flaw in the picture. It was one of the things that made the picture work. Aristotle took a very different view. He rejected the idea of a true vacuum and argued that nature abhors a vacuum, a phrase that has echoed through history with impressive stamina. In Aristotle's view, a completely empty void was not just unlikely, it was deeply problematic. Motion, causation, and the structure of the natural world seemed hard to make sense of if a perfect nothing could exist. For many centuries, that suspicion shaped how educated people thought about space. Emptiness was not merely a gap, it was a philosophical problem. That old disagreement matters because it shows this is not a modern gimmick. The puzzle at the heart of the title has roots that stretch back more than 2,000 years. Is space a real thing in its own right? Can there be a region with truly nothing in it? Or does the very attempt to imagine such a place fall apart under scrutiny? Those questions passed from philosophy into natural science, then from natural science into physics, and eventually into the quantum world, where the answers became stranger than either Democritus or Aristotle could reasonably have predicted. The reason the issue became so important is simple. If empty space is possible, then the universe contains absence as well as presence. If empty space is impossible, then what appears to be empty must always contain something, whether visible or invisible, material or structural. That is not a small detail. It shapes how matter moves, how forces act, how waves travel, and how the universe itself is understood. In other words, the definition of nothing turns out to affect the definition of almost everything. This also explains why the question belongs not only to ancient philosophy, but to classical physics, relativity, and quantum theory. Each era inherited the same basic mystery and answered it differently. At first the question was whether emptiness could exist at all. Later the question became what properties empty space might have. Then, with relativity, space stopped looking like a passive backdrop and began to look like something with geometry and physical meaning. And with quantum physics, the old quiet vacuum became something far more subtle, something that cannot simply be treated as a clean absence. That change in meaning is the heart of the journey. Human intuition begins with an empty room. Physics eventually arrives at the quantum vacuum. Those are not the same idea wearing different clothes. They're genuinely different concepts. One belongs to everyday experience, the other belongs to a world in which fields, energy states, and the rules of quantum theory matter more than visual common sense. So the safest way to begin is with a careful distinction. Ordinary emptiness means no familiar objects are present. The quantum vacuum means a lowest energy state of physical fields, even when no particles are around in the usual sense. That may sound like a technical refinement, but it changes everything. A room can look empty and still be full of air. Interplanetary space can look empty and still contain sparse gas, radiation, magnetic fields, and gravity. And even if all of that is stripped away in thought, modern physics still does not arrive at a simple blank nothing, which is why the question refuses to stay simple. The more carefully emptiness is examined, the less empty it becomes. And before quantum physics could make that claim in its own peculiar language, earlier physics first had to wrestle with a more basic issue: whether a vacuum was possible in the first place, and whether nature would allow even a small patch of genuine emptiness to exist. Once philosophers had spent centuries arguing about whether emptiness could exist, science began doing something far more troublesome for philosophy. It started testing the question. This was a rather rude development for pure speculation. It is one thing to debate the vacuum while standing in a tunic and making bold claims about nature. It is another to fill glass tubes with mercury, turn them upside down, and discover that nature may not be quite as horrified by empty space as once advertised. A major turning point came in the 17th century with Evangelista Torricelli. Torricelli was interested in pumps, pressure, and the practical problem of why water could only be lifted so high. That does not sound dramatic at first glance, but many profound discoveries begin with people being mildly annoyed by equipment. Torricelli realized that mercury, being much denser than water, could be used to test the same pressure effect in a shorter column. He filled a long glass tube with mercury, sealed one end, inverted it into a dish of mercury, and observed that the mercury level in the tube dropped, leaving an apparently empty space above it. That space became famous. It was not merely a gap in a pipe or a missing puddle. It looked like a region containing no air and no visible material at all. Torricelli had, in effect, produced an artificial vacuum, or at least something very close to one by the standards of the time. He argued that the mercury column was supported by the pressure of the atmosphere pressing on the dish below, not by any mysterious suction from above. The empty region at the top of the tube was therefore not an accident. It was part of the explanation. This mattered enormously, because it moved the conversation from philosophy into measurement. The old phrase that nature abhors a vacuum was now facing a difficult question. If nature truly hated vacuums, why was one sitting calmly at the top of a mercury tube, causing no visible distress apart from perhaps some wounded pride among older ideas? Blaise Pascal pushed the matter further. He understood that if atmospheric pressure was supporting the mercury column, then the height of that column should change with altitude, because the weight of the air above would be different on a mountain than at lower ground. This was an elegant idea because it tied the experiment to the physical world in a testable way. If the column changed with height, then the atmosphere itself was doing the work. Pascal arranged for measurements to be taken at different elevations, including on the Puy de Dôme in France. The mercury column did indeed fall as altitude increased. This was a quiet revolution. The vacuum was no longer just a philosophical curiosity. It was wrapped up with pressure, measurement, instrumentation, and the physical behavior of air. Empty space, or at least near empty space, had become something science could produce, study, and reason about quantitatively. The vacuum was not yet the quantum vacuum of modern physics, but it had already ceased to be a purely abstract nothing. Even at this stage, however, the situation remained more subtle than it first appeared. A laboratory vacuum in the 17th century was not perfect emptiness. There were always traces of material, imperfections in the apparatus, and limits to what could be removed. But that almost did not matter. The real shift was conceptual. Nature could contain regions that were emptier than ordinary experience suggested. The vacuum had become a legitimate scientific topic. From there, the question changed form. It was no longer only whether a vacuum could exist. It became what space itself was. If a region could contain no ordinary matter, was that region still something real, or was it just a way of talking about the absence of things? Isaac Newton gave one of the most influential answers. In Newton's framework, space was absolute. It existed independently of the objects within it. Matter moved through space, forces acted across space, and time flowed uniformly in the background. Space was the stage, and the physical world was the performance taking place upon it. Even if the stage were empty, the stage itself remained. In that sense, Newton had no deep problem with empty space. A vacuum could exist because space did not need to be made out of ordinary material in order to be real. This picture was enormously successful. Newtonian mechanics described motion, gravity, and planetary orbits with extraordinary power. It gave science a stable arena in which matter could move predictably. Yet the very neatness of that arena also made some thinkers uneasy. If space was absolute, what exactly was it? Could something that had no substance, no texture, and no obvious mechanism still count as physically real? Or was absolute space simply a useful framework for calculation? These questions simmered for a long time, but they became especially urgent in the 19th century, when physics began to understand light in a new way. James Clerk Maxwell transformed the story by unifying electricity and magnetism into a single theory of the electromagnetic field. Maxwell's equations showed that changing electric fields and changing magnetic fields could sustain one another and travel through space as waves. Those waves moved at a speed that matched the measured speed of light. The conclusion was profound. Light was an electromagnetic wave. That raised a new problem almost immediately. Waves, as people then understood them, usually needed something to wave in. Water waves travel through water. Sound waves travel through air or other material. Vibrations pass through strings, solids, or fluids. So if light was a wave, what medium was waving when light crossed apparently empty space from the sun to Earth? The proposed answer was the luminiferous ether, often just called the ether. This was imagined as an all-pervading medium filling space, subtle enough not to block planets, transparent enough not to interfere with ordinary matter, and rigid enough in some sense to support electromagnetic waves. It was an awkward invention, though an understandable one. Scientists were trying to preserve the intuition that waves require a medium. If light travelled through space, then space apparently could not be truly empty. Something had to be there. For a while, the ether seemed like a reasonable solution. It allowed light to remain wave-like without giving up familiar mechanical instincts. But it also produced a growing list of conceptual headaches. If Earth moved through the ether as it orbited the Sun, then the measured speed of light might differ depending on direction, much as a moving observer experiences a wind differently depending on orientation. This became testable. In the late 19th century, Albert A. Michelson and Edward W. Morley carried out the most famous attempt to detect Earth's motion through the ether. Their interferometer experiment was designed with remarkable sensitivity for its time. Light beams were sent along different paths and recombined so that tiny shifts in travel time could reveal motion through the supposed ether wind. If Earth were moving through a stationary luminiferous ether, then light should take slightly different times along different directions, and the interference pattern should shift accordingly. But the expected shift did not appear. This result became one of the most famous null results in the history of science. Null results can sound disappointing, but they are often explosive in their consequences. Michelson and Morley did not merely fail to find a detail. Their experiment struck at the heart of the medium that many physicists thought light required. The ether became harder and harder to defend in its old mechanical form. That did not mean everyone instantly abandoned it. Physics is not usually so tidy. Various modified ether theories were proposed, and for a while the idea survived through increasingly elaborate adjustments. But the deeper lesson was becoming unavoidable. Perhaps empty space did not need a material medium of the old sort. Perhaps light could propagate without the universe being filled with an invisible fluid or elastic substance, behaving like an absurdly overqualified ghost. By this point, the concept of empty space had changed several times. It began as a philosophical possibility, then became a laboratory achievement, then a stage for mechanics, and then a puzzle for electromagnetism. Empty space was no longer a simple absence. It was an active scientific problem. Experiments, theories, and measurements were all pressing on it from different directions. That pressure set the stage for an even more radical shift. The old passive backdrop of Newton would not survive unchanged. The failed search for a luminiferous ether, the growing power of Maxwell's theory, and the deep questions surrounding motion and light were pushing physics toward a new view. In that new view, space would no longer be a silent container waiting politely for matter to occupy it. It would begin to acquire structure, geometry, and physical significance of its own. And once that happened, the road toward the quantum vacuum would become much easier to imagine, even if not yet any easier to explain. By the beginning of the 20th century, physics had reached an awkward and fascinating point. Newton's picture of absolute space had been enormously successful, and Maxwell's theory had revealed light as an electromagnetic wave, yet the old intuitive picture of space as a silent, rigid backdrop was beginning to look less secure. The failed search for the luminiferous ether had removed one familiar support. Something had to replace it. That replacement arrived through Albert Einstein, and it changed not only the meaning of motion and time, but the meaning of space itself. Einstein's special relativity, published in 1905, began from a deceptively simple demand. The laws of physics should look the same for observers moving at constant speed relative to one another, and the speed of light in a vacuum should be the same for all such observers. Those statements may sound modest at first, but together they forced a dramatic revision of everyday intuition. Time could no longer be universal in the old Newtonian sense. Distances could no longer remain fixed and absolute for all observers. Space and time, once treated as separate and stable, began to interlock. This was one of the most profound conceptual shifts in the history of science. Space was no longer just where things were, and time was no longer just what clocks measured in the same universal rhythm for everyone. Instead, the two became parts of a single structure: space-time. Events were described not merely by position or by time alone, but by their place within this four-dimensional framework. Different observers could disagree about distances and durations, yet the deeper structure of space-time preserved the laws of physics. This mattered for the question of emptiness, because it quietly removed the idea that empty space was a passive container waiting to be occupied. Even in special relativity, space was already tied to time in a way that made the old stage-like metaphor feel incomplete. The geometry of the world was not just scenery, it was part of the physical description. Still, special relativity did not yet provide a new theory of gravity. It dealt with observers in uniform motion and with the deep structure required by the speed of light. But it did not explain why planets orbit stars or why apples, with admirable consistency, refused to float off into the afternoon. Einstein's next step was even more radical. In General Relativity, published in 1915, gravity ceased to be a mysterious pulling force reaching across empty space. Instead, gravity became a feature of space-time geometry itself. Matter and energy tell space-time how to curve, and curved space-time tells matter how to move. That sentence has become famous partly because it is elegant and partly because it saves everyone from immediately having to wrestle with tensor mathematics before tea. The central idea is clear even without the formal machinery. Massive objects such as stars and planets do not simply sit in space and exert force through it, like invisible puppeteers tugging strings. Their presence changes the geometry of space-time around them. Motion that would otherwise be straight becomes curved because the underlying structure through which objects move is itself curved. A planet orbiting the sun is not being yanked by an unseen rope. It is following the natural paths permitted by the curved space-time around a massive body. That shift transformed the meaning of empty regions. In Newton's picture, a vacuum could still be treated as a sort of blank arena. In Einstein's general relativity, even a region containing no planets, no stars, no gas, and no dust could still possess structure. Space-time itself could be curved. It could expand. It could bend the paths of light. It could carry information about gravity without requiring any visible material to fill the region. This is a crucial point. Empty of matter does not mean empty of geometry. A region of space with no obvious contents may still be physically rich in the relativistic sense. Light passing through such a region can be deflected if space-time is curved. Clocks can tick at different rates depending on gravitational conditions. Distances can evolve as the universe expands. None of that requires a visible medium in the old ether-like sense. The structure belongs to space-time itself. One of the most striking consequences of this view is the existence of gravitational waves. These are ripples in space-time produced by accelerating masses, especially violent events such as merging black holes or neutron stars. When such objects move in extreme ways, they disturb space-time and send those disturbances outward at the speed of light. These waves can pass through regions that appear otherwise empty, stretching and squeezing distances by astonishingly small amounts as they travel. That is not just a theoretical curiosity. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made the first direct detection of gravitational waves, a result announced in 2016. The signal came from two merging black holes more than 1 billion light-years away. Later detections were also made with the participation of the Virgo collaboration in Europe. These observatories measured changes in length far smaller than an atomic nucleus across arms kilometers long. It is hard to overstate how extraordinary that is. Regions of space that looked utterly empty were shown to be carrying real, measurable distortions in space-time itself, so by the time relativity had done its work, empty space was already much less empty than common sense had imagined. It could possess geometry. It could curve in response to mass and energy. It could expand across the cosmos. It could ripple and transmit gravitational waves. The vacuum, in the old everyday sense of nothing there, had already become physically active before quantum theory arrived to complicate it further. At the same time, it is important to keep the different layers of the story distinct. The structure described by relativity is not yet the same thing as the quantum vacuum. Curved space-time and quantum fields are not interchangeable ideas. General relativity tells a story about geometry, gravity, and the large-scale structure of the universe. Quantum theory, which will soon enter the picture, tells a story about discreteness, uncertainty, states, and fields behaving in ways that classical intuition struggles to follow. Both change the meaning of emptiness, but they do so in different ways. Relativity shows that a region can be empty of matter and still not be physically blank. That is already a major conceptual step. It loosens the old intuition that emptiness must mean featurelessness. It teaches that absence of visible stuff does not imply absence of structure, behavior, or measurable effects. Space, now joined with time as space-time, has properties of its own. It is not a silent void in the old philosophical sense. It is dynamic, relational, and part of the physical world. That lesson prepares the mind for the next and perhaps stranger move. Once physics accepts that space is not merely a passive stage, it becomes easier to accept that the deepest quiet may not be truly quiet at all. Relativity made space dynamic. Quantum mechanics would go further. It would begin to challenge the very idea that a physical system could ever settle into perfect stillness, and that challenge would eventually turn the vacuum from a geometrical setting into something even more surprising, a state that cannot simply be reduced to nothing. By the early 20th century, physics had already learned to distrust common sense, but it had not yet stopped hoping that the universe might still behave, underneath all the complications, like a very elegant machine. A strange machine, perhaps, a subtle machine, but still a machine in the classical sense. Smooth causes leading to smooth effects. Precise positions and precise motions existing, whether anyone measured them or not. A world in which the deepest reality was definite, even if human beings were occasionally too clumsy to notice. Quantum theory ruined that comforting picture with extraordinary thoroughness. It did not arrive all at once. It emerged in pieces, each one initially looking like a local repair to a specific problem, and each one eventually helping to overturn the whole conceptual furniture of physics. The first major crack is usually traced to Max Planck in 1900. Planck was studying black-body radiation, the light emitted by hot objects, and the calculations of classical physics were failing badly. They predicted that a hot object should pour out absurd amounts of energy at short wavelengths, a disaster later nicknamed the ultraviolet catastrophe. To make the formulas agree with observation, Planck introduced a radical idea almost reluctantly. Energy, at least in this context, had to be exchanged in discrete packets rather than as a perfectly continuous flow. This was the beginning of quantization. The world, at a fundamental level, was refusing to behave as a smooth continuum in every respect. Planck did not immediately present this as a total revolution in reality, but the door had been opened, and once opened, it proved extremely difficult to close again. Albert Einstein pushed that door much wider in 1905 when he explained the photoelectric effect. Light had long been understood as a wave, especially after the success of James Clerk Maxwell's electromagnetic theory. But Einstein showed that in some circumstances light behaved as though it came in localized packets of energy, later called photons. This was deeply unsettling. Light, which had seemed securely wave-like, now displayed particle-like behavior as well. Nature was not choosing one tidy category and staying there. Niels Bohr added another blow to classical intuition in 1913 with his model of the atom. Electrons, instead of orbiting the nucleus with any arbitrary energy, could occupy only certain allowed states. They could jump between these levels, emitting or absorbing light in discrete amounts. Again, the old smoothness failed. Atomic reality turned out to be structured in steps, not sliding continuously like a bead on a wire. As the new theory developed, the classical picture became harder to defend. Werner Heisenberg, Erwin Schrödinger, Max Born, Paul Dirac and others helped construct what became modern quantum mechanics. Heisenberg introduced matrix mechanics. Schrödinger developed wave mechanics. Born clarified the probabilistic interpretation of the wave function. Dirac unified quantum ideas with relativity in ways that would later prove crucial for quantum field theory. These were not minor adjustments to Newtonian habits. They were signs that the deep logic of nature had changed. The broad shift can be stated simply, though it took physics years to absorb. In classical mechanics, a system is described by definite quantities such as position and momentum evolving continuously through time. In quantum mechanics, a system is described by a state, and what can be predicted are probabilities for different measurement outcomes. The theory does not merely say that human beings are ignorant of hidden exact details in the usual classical way. It says that the physical description itself is organized differently. Possibilities, amplitudes, allowed states, and quantized excitations become central. The universe at small scales is not just a tiny version of the familiar world. It plays by stranger rules. That change matters enormously for the idea of emptiness, because in classical thinking, nothing happening is easy to imagine. A classical object can simply sit still. A pendulum can hang at rest. A particle can remain motionless in a calm, featureless state. Classical stillness is conceptually straightforward. Quantum stillness is not. One of the clearest reasons is the uncertainty principle, introduced by Werner Heisenberg in 1927. This principle states that certain pairs of physical quantities cannot both be known with unlimited precision at the same time. The most famous example is position and momentum. The more sharply one is defined, the less sharply the other can be fixed. This is not merely a problem of bad instruments or human clumsiness. It is built into the structure of quantum theory itself. That point is crucial. In ordinary life, uncertainty usually means ignorance. A person might not know where the keys are because the keys have been placed somewhere mysterious, usually by that same person a few hours earlier. Quantum uncertainty is not like that. It is not simply a practical failure to keep track of details. It is a limit built into how physical states can exist. This immediately changes what it means for a system to be perfectly quiet. In classical physics, one might imagine fixing both the position and motion of something exactly, pinning it into total stillness. Quantum mechanics refuses that neat arrangement. If a particle were confined in some way, its momentum could not also be perfectly definite. If its motion were reduced too far in one sense, the uncertainty in another quantity would grow. The classical dream of a totally frozen microscopic world begins to fall apart. It is important not to overstate this in a sloppy way. Quantum mechanics does not mean that everything is chaotically flying around in a permanent carnival of nonsense. The theory is highly precise, mathematically powerful, and astonishingly successful. What it changes is the meaning of calm. A quantum system can have a lowest possible energy state, a ground state, but that does not automatically mean all motion-like features vanish in the classical sense. The system cannot always be reduced to a state of exact featureless stillness. There remains an irreducible quantum character even in the lowest allowed condition. This is the seed of the later story about empty space. The point here is not yet to explain the full quantum vacuum. The point is simpler and more important. Once quantum theory enters the scene, the old classical idea that the deepest level of reality can sit in perfectly motionless silence becomes unreliable. That matters because empty space, if it is going to be described physically, can no longer be assumed to behave like a passive blank with everything turned off. Historically, one of the best-known ways physicists tried to make sense of this new framework was the Copenhagen interpretation, associated especially with Niels Bohr and Werner Heisenberg. In this broad family of views, the quantum state is tied to the probabilities of measurement outcomes, and quantum properties are not treated as possessing definite classical values in the old straightforward sense independent of experimental context. Different interpretations of quantum mechanics still exist and are debated today, but for the present purpose, the interpretive battles are less important than the shared empirical lesson. No matter which philosophical language one prefers, quantum systems do not behave like miniature clockwork objects with fully classical quietness available in the background. That shared lesson was confirmed again and again through experiments, from atomic spectra to electron diffraction, and later through the entire astonishing success of modern quantum physics. Tiny entities behaved as though wave-like and particle-like descriptions had to be woven together. States came in allowed forms. Measurement outcomes followed precise probabilities. Systems retained behaviour that classical language could only approximate awkwardly. And that is why quantum physics could never really leave space alone. Once the microscopic world is governed by quantum rules, it is not enough to describe matter alone in this new way, while leaving the background untouched as a perfectly inert classical emptiness. If the constituents of reality obey quantum principles, then the deeper framework in which those constituents exist begins to look different as well. The logic spreads. The disturbance reaches the foundation. The old vacuum had already been weakened by relativity, which showed that empty regions could have geometry, curvature, and physical significance. Quantum mechanics now added a new kind of pressure. It suggested that at fundamental scales, the notion of a perfectly silent physical state was itself suspect. If physical systems cannot simply be frozen into exact classical stillness, then any serious later attempt to describe empty space will have to face an uncomfortable possibility. What if space is not merely a location where quantum things happen? What if the fields that fill space, even in their lowest possible state, can never be made completely still either? To understand why quantum physics says empty space is full, it becomes necessary to meet the real inhabitants of modern physics. And, rather inconveniently for ordinary intuition, those inhabitants are not little hard particles flying through a blank void like grains of dust in sunlight. That image is useful at times, and it survives in schoolbooks because it is simple and friendly and asks very little of the imagination. But it is not the deepest picture modern physics offers. At the most fundamental level currently known, the real characters are fields. A field is a physical quantity assigned throughout space and time. That may sound abstract at first, but the basic idea is not as exotic as it seems. Temperature in a room can be described as a field, because each point in the room can in principle have a temperature. Wind speed across the sky can be described as a field, because each location has a value and direction. A gravitational field tells how gravity acts from place to place. An electric field tells how electric forces would affect a charged object at different points in space. The important step is this. In modern particle physics, fields are not just useful bookkeeping devices. They're treated as physically real ingredients of the world. Instead of imagining particles as the primary objects and fields as secondary influences around them, the deeper framework turns the picture inside out. The fields come first. What people call particles are excitations of those fields. That sentence carries most of the strangeness of the modern view. An electron is not best pictured as a tiny permanent bead, existing independently and merely moving through space. In quantum field theory, the electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field, more precisely the quantized field associated with electromagnetism. Quarks are excitations of quark fields. Gluons are excitations of the gluon field. In other words, what looks like a particle is what happens when a field is excited in a particular quantized way. This is why the question of empty space changes so dramatically. If fields extend throughout space, then space is not an empty container waiting to be filled by particles from time to time. Space is already occupied in a physical sense by the fields themselves. Even when no particles are present in the familiar visible way, the fields remain. They are not occasional visitors, they are the continuing background reality. This framework is called quantum field theory. It is one of the central achievements of modern physics. Quantum field theory combines the principles of quantum mechanics with the demands of special relativity, allowing physicists to describe matter and forces at fundamental scales in a way that respects both quantization and the finite speed of causal influence. It is not a fringe idea, not a speculative side road, and not the sort of thing supported only by one confident professor in a dramatic lecture hall. It is the working language behind much of modern particle physics. The most successful large-scale application of quantum field theory is the Standard Model of particle physics. The Standard Model is the central framework used to describe known fundamental particles and 3 of the 4 fundamental interactions: electromagnetism, the strong nuclear interaction, and the weak nuclear interaction. Gravity sits awkwardly outside this framework, which is one reason physicists continue searching for a deeper unification. But within its domain, the Standard Model is one of the most accurate scientific theories ever constructed. Institutions such as CERN, home of the Large Hadron Collider, test this framework with astonishing precision. Particle accelerators do not merely smash little balls together to see what crumbs fall out, although that is the version most likely to make sense before breakfast. What they are really doing is exciting underlying fields under controlled extreme conditions, creating particles as quantized disturbances that can then be detected, measured, and compared with theoretical predictions. The remarkable agreement between theory and experiment is one reason physicists take the field picture so seriously. It helps to linger with this idea because it replaces a very old habit of thought. The ordinary imagination wants to ask where particles are. Quantum field theory invites a different question. Which fields are present and what state are they in? That shift is not just philosophical decoration. It changes the meaning of what exists in a region of space. Consider the electron field. It is not turned on only when an electron happens to pass by. It exists everywhere. The same is true for the quark fields, the photon field, the gluon field, and the other fields of the Standard Model. Not all of them behave in identical ways, and not all are easy to visualize, but the crucial point remains the same. They are not local little objects scattered sparsely across an otherwise blank universe. They are extended components of physical reality. The photon field deserves a moment of special attention, because it helps bridge older ideas with modern ones. Maxwell had already shown in the 19th century that light is electromagnetic in nature. Quantum field theory takes that further by treating light as quantized excitations of the electromagnetic field. A beam of light is not a stream of tiny solid pellets shot across emptiness in the ordinary sense, nor is it just a smooth classical wave. It is the behavior of a quantized field. That field persists even when no visible light is present. The strong nuclear interaction is described through quantum chromodynamics, often shortened to QCD. Here the key fields include quark fields and the gluon field. Quarks are never ordinarily found in isolation because the strong interaction confines them inside composite particles such as protons and neutrons. Gluons mediate the strong force, binding quarks together. This may sound very far from the question of empty space, but it matters because it reinforces the central lesson. Matter is not built from isolated eternal pebbles. It is built from field excitations arranged and bound in specific ways. The weak nuclear interaction involves additional fields associated with the W boson and Z boson, which are essential in processes such as radioactive beta decay. Then there is the Higgs field, which will become especially important later. The Higgs field is not merely another particle source in the list. It has a distinctive role in the structure of the Standard Model because its background value helps give mass to certain fundamental particles. Even this brief preview is enough to hint at how peculiar the vacuum will turn out to be. A field can matter even when nothing dramatic appears to be happening. This is where the older idea of empty space finally begins to collapse under the weight of modern theory. If reality is fundamentally composed of overlapping fields extending throughout the universe, then a region with no visible particles is not a region with no physical content. It is a region in which the fields are present without obvious localized excitations. That is already a profound revision. The emptiness is no longer absolute. The silence is not the same as absence. An analogy can help, provided it is not taken too literally. Imagine an ocean on a perfectly calm day. A wave might pass, and you would notice a visible disturbance. But even when no obvious wave is present, the ocean still exists. Its depth, tension, and capacity for motion remain. Now make the analogy much stranger and more precise. In quantum field theory, the universe is not empty space with a few occasional ripples. It is more like a vast overlapping set of oceans, each one corresponding to a different field, each one present everywhere, each one capable of excitations that appear to us as particles. Of course, even that image has limits. Fields are not fluids in the ordinary sense, and the vacuum is not a liquid sea sloshing about in cosmic moonlight. But the analogy does useful work because it helps the mind stop treating particles as the only things that count as real. The field is not secondary to the ripple. The ripple depends on the field. This matters not just for abstract theory, but for the entire logic of the title. When people hear that empty space is full, they often picture hidden matter, invisible dust, or some sort of faint undetected fog. Quantum field theory points elsewhere. Empty space is full because the fields are there whether or not particles are visibly passing through. It is full in the sense of being physically structured, continuously occupied by the underlying ingredients from which particle-like phenomena emerge. And once that picture is accepted, a sharper question begins to form. If fields are always present, then what counts as their quietest possible condition? What does emptiness mean in a world where the basic ingredients never leave the stage? If a region contains no obvious particles, the fields still remain. So the real issue is no longer whether space contains anything at all. The real issue is what those fields are doing when they're in their lowest possible state, when no extra excitations seem to be present, when the universe appears by every ordinary standard to be as empty as it can be. Because in quantum physics, even that deepest level of quiet turns out not to be truly still. Once fields become the real characters, the meaning of emptiness has to change again. A region of space can no longer be described simply by asking whether particles are present in the ordinary visible sense. The deeper question becomes, what state are the fields in? And the answer to that question leads directly to one of the most important ideas in modern physics. The vacuum is not a condition of absolute nothingness. It is the lowest energy state of the fields. That distinction is the heart of the whole subject. It deserves to be stated slowly and clearly, because almost every misunderstanding about empty space begins here. The quantum vacuum is not literal non-existence. It is not the total absence of reality. It is not a blank metaphysical nothing beyond physics altogether. It is a state within a physical system. More precisely, it is the ground state, the lowest energy state available to the fields that fill space. That means the vacuum belongs to the theory. It is part of the structure of the world being described. It is not outside the system. It is the calmest state the system can physically have. That may sound like a technical refinement, but it changes everything. In ordinary language, the word vacuum suggests emptiness in the absolute sense, a hoovered-out gap, a cosmic cupboard with nothing left inside. Physics uses the word differently. In quantum field theory, the vacuum is what remains when no extra particles are present, and the fields have settled into their lowest allowed condition. The fields are still there, the system is still there, the laws are still there. The vacuum is not nothing, it is the quietest possible something. This is why the title begins to make literal scientific sense. Empty space is full not because it hides ordinary material, but because what appears empty is actually the vacuum state of real fields. The emptiness is a physical condition, not an absence of all conditions. It is a state of the world, not the disappearance of the world. To see why this matters, it helps to think about the idea of a lowest energy state more carefully. In classical physics, a lowest energy state often suggests perfect rest. A ball at the bottom of a bowl sits still. A pendulum hanging straight down remains motionless if undisturbed. The system is settled. The energy is minimized, nothing more is happening. Classical intuition therefore encourages a very simple expectation. If the fields are in their lowest possible state, then surely everything should be completely still. Quantum theory refuses that expectation. The reason goes back to the uncertainty principle and to the broader structure of quantum states. A quantum system cannot in general have all the neat classical properties one might wish to assign to it with unlimited precision. There is a limit to how sharply certain quantities can be fixed together. As a result, the lowest energy state of a quantum system is not always a state of complete stillness in the classical sense. There remains an irreducible residual character to the system, a kind of unavoidable background activity built into the fact that it is quantum. This residual energy is called zero-point energy. The name is wonderfully plain for such a strange idea. It means the energy that remains even at the lowest point, even when no further energy can be removed without changing the nature of the state itself. In everyday thinking, zero is the place where things stop. In quantum theory, the deepest accessible calm often still carries a minimum amount of energy. The system cannot be drained into perfect classical silence. A simple example helps. One of the most famous model systems in physics is the quantum harmonic oscillator. The phrase sounds forbidding, but the underlying picture is quite gentle. It is the quantum version of something like a mass on a spring, a system that in classical physics can move back and forth around an equilibrium point. In the classical description, the lowest energy state is easy to imagine. The mass sits exactly at the equilibrium point with no motion at all. Position fixed, momentum zero, perfect calm, a spring having the most uneventful day possible. The quantum version is different. In quantum mechanics, the oscillator cannot sit with both perfectly definite position and perfectly definite momentum. If it were pinned exactly at the equilibrium point with no uncertainty in position, the uncertainty in momentum would become too large. If momentum were fixed too precisely, position would become uncertain. The ground state therefore becomes a compromise built into the theory. It is the lowest energy state, yes, but not a state of classical stillness. It has an irreducible spread. The oscillator retains zero-point energy. That example is not just a mathematical curiosity kept alive by textbooks and stubborn lecturers. It teaches a general lesson. Quantum systems resist complete stillness. The lowest allowed state is not identical to the complete absence of dynamical character in the classical sense. There is always a floor beneath which the energy cannot fall. The system can be calm, but not classically frozen. Now carry that lesson into the world of fields. A quantum field can be thought of very roughly as an enormous collection of oscillatory modes spread across space. Again, there is no need to drown peacefully in formalism here. The essential point is enough. If each mode of a quantum field behaves in a way that resembles a quantum oscillator, then each mode can contribute its own lowest state residual energy. The vacuum of the field is therefore not a perfect featureless blank. It is the collective ground state of those quantum degrees of freedom. This is why the vacuum still belongs to a real physical system. It is not a whole outside reality. It is what the fields are doing when nothing extra has been added. The electron field in its ground state is still the electron field. The electromagnetic field in its ground state is still the electromagnetic field. The gluon field in its ground state is still the gluon field. No visible particles may be passing by, yet the fields themselves remain present as part of the physical world. It also becomes clear why lowest energy does not mean zero content in the everyday sense. If someone says a theatre is empty, the ordinary implication is that nobody is there. But if the theatre still has walls, air, seats, tension in the materials, faint electrical hums in the lighting system, and a stage ready for performance, then physically it is not nothing at all. It is merely unoccupied in one specific everyday sense. The quantum vacuum is a bit like that, though much deeper and stranger. It is empty of particle excitations in the usual sense, but it is not empty of the fields themselves, nor empty of the structure of their ground state. This is the first direct answer to the central question. Why does quantum physics say empty space is full? Because what looks empty is the vacuum state of underlying fields, and that vacuum state is not identical to non-existence. It is the lowest energy configuration available to a physical system that is still very much there. Empty space is therefore not the absence of fields. It is what the fields look like when they are as quiet as quantum law allows. That phrase matters too, as quiet as quantum law allows. Not as quiet as classical imagination would prefer. Quantum theory sets the rules, and the rules do not permit the kind of perfect frozen stillness that older intuition might expect. 0-point energy remains. Ground states remain physical. The vacuum remains part of the universe, not the subtraction of the universe. At this stage, the picture has changed completely. Space is no longer a bare container. Fields fill it. Particles are excitations of those fields. And even when no such excitations are present, the fields do not vanish into absolute nothingness. They settle into their vacuum state, their ground state, their lowest allowed condition. That state is physically meaningful, mathematically structured, and experimentally important. And once the vacuum is understood this way, as an active ground state rather than a metaphysical blank, another idea starts to feel less outrageous than it first sounded. If the fields remain present even in emptiness, and if their lowest state still carries irreducible quantum character, then perhaps empty space is not merely quiet. Perhaps it is quietly restless. Perhaps the vacuum can exhibit subtle fluctuations, temporary excitations, and measurable effects that arise precisely because the ground state of a quantum field is not the same thing as nothing at all. Once the vacuum is understood as the lowest state of real quantum fields, a new idea enters the story, and it is one of the most famous and most badly abused ideas in modern physics. This is the idea of vacuum fluctuations. The phrase sounds dramatic, which is partly why it has had such a successful career outside physics. It can easily be made to sound like empty space is a kind of magical bubbling cauldron, throwing tiny objects in and out of existence like a cosmic kettle with no regard for sanity. That image is memorable, but it is also dangerous if taken too literally. The real idea is subtler, more constrained, and far more interesting than a simple picture of miniature fireworks in the void. What physicists mean is this. The vacuum is the ground state of quantum fields, but that ground state is not a perfectly rigid classical stillness. Because the fields are quantum objects, their lowest state still involves irreducible quantum behavior. The vacuum, therefore, has structure, correlations, and dynamical features that show up in calculations and, importantly, in observable effects. In other words, the vacuum is not a dead backdrop. It is a quantum state, and quantum states do not behave like silent classical emptiness. One reason this idea is often explained badly is that people reach quickly for the uncertainty principle, and then immediately sprint far beyond what it safely says. There is indeed an uncertainty relation involving energy and time, and it is often used as a rough guide in popular explanations, but it needs care. The relation does not mean energy can simply be borrowed from nowhere for a brief moment with no questions asked, as though the universe were running an extremely relaxed accounting system. Physics is not that casual. The energy-time uncertainty relation is not identical in status to the better-known relation between position and momentum. Time in ordinary quantum mechanics is not represented in quite the same way as position or momentum, so the statement must be handled more carefully. In practice, physicists often use energy time reasoning heuristically, meaning as a useful guide within broader calculations, not as a magic slogan that explains everything. This matters because the popular phrase, "particles pop into existence because the uncertainty principle allows it," often creates more confusion than clarity. A safer and more accurate way to think about vacuum fluctuations is to start with the fields themselves. A quantum field has modes, and those modes behave in ways that resemble quantum oscillators. Even in the ground state, those modes are not classically silent. Their properties cannot all be pinned down as though they were resting mechanical parts. The vacuum state therefore contains unavoidable quantum uncertainty and non-zero structure. Fluctuations are not an optional decoration added afterward. They are part of what it means for the vacuum to be a quantum state rather than classical nothingness. This is why the vacuum can influence physical systems. If it were truly nothing in the strictest sense, it could not affect anything, because there would be nothing there to do the affecting. But the quantum vacuum does affect things. The fluctuating nature of fields enters calculations in quantum electrodynamics, quantum chromodynamics, and the broader machinery of quantum field theory. These are not poetic suggestions. They are part of the working framework used to predict measurable phenomena with extraordinary precision. At this point, the famous phrase, "virtual particles popping in and out of existence," usually arrives, often with great enthusiasm and very little supervision. This image is not completely useless, but it must be handled carefully. In some calculations, especially in perturbation theory, physicists use internal lines in Feynman diagrams that are often described informally as virtual particles. These are not ordinary particles flying around in the same sense as detectable particles in a beam or a detector. They are elements within a mathematical description of interactions. They help organize the calculation. They are not always best understood as literal tiny objects briefly visiting reality before slipping away like embarrassed guests. That distinction matters. If the phrase is taken too literally, it creates a cartoon version of the vacuum, as though empty space were constantly spraying real little particles everywhere, in the way sparks leap from a fire. That is not a faithful picture. The vacuum is restless, yes, but not in a childish or cinematic way. The better claim is that quantum fields in their ground state possess non-trivial structure, and this structure can be described mathematically in terms of fluctuations, correlations, and contributions to observable effects. That may sound less flashy, but it is much closer to the truth, and the truth is quite strange enough already. A useful comparison might help. Imagine listening to what seems at first like silence in a large building at night. At the level of casual human attention, it feels quiet. But as listening sharpens, the silence is revealed to contain faint electrical hums, distant movements of pipes, the settling of materials, currents of air, and vibrations too subtle to notice at first. The silence was never really blank. It was structured quiet. The quantum vacuum is something like that, except more fundamental and vastly more exacting. It is not noisy in the everyday sense, but it is not featureless either. This is also the moment when the title becomes richer. It is no longer enough to say that empty space is full, because fields are present everywhere. That is true, but incomplete. The deeper claim is that those fields remain dynamically unsettled even in their lowest state. They do not become classical nothing. Their ground state carries quantum character that can influence the behavior of matter, radiation, and physical systems more broadly. Empty space is full not just because something remains there, but because what remains is active in a specifically quantum sense. It is worth emphasizing once more that this does not open the door to anything goes fantasy. Vacuum fluctuations are not a license to claim that anything imaginable can burst into existence if one says the word quantum with sufficient confidence. The theory is precise. The permitted behavior is tightly constrained by the mathematics of quantum field theory and by experiment. That precision is part of what makes the subject so remarkable. The vacuum is strange, but it's not random nonsense wearing scientific makeup. And that brings the story to an important test. In physics, the most persuasive strange ideas are the ones that leave evidence behind. It is one thing to say that the vacuum has structure, fluctuations, and quantum activity. It is another to show that these claims produce measurable consequences in the world. If the vacuum is real in this physical sense, if empty space is genuinely active rather than merely redefined by clever language, then it should leave fingerprints. It should alter forces, shift energy levels, and change what happens in carefully designed experiments. And it does. One of the most elegant ways physics shows that empty space is not just a philosophical trick is through an effect so delicate that it almost sounds fictional when first described. This is the Casimir effect, named after the Dutch physicist Hendrik Casimir, who predicted it in the late 1940s. It has become one of the most famous windows into vacuum physics because it turns a strange theoretical idea into something with measurable force. The setup is beautifully simple in outline. Imagine two very flat conducting plates placed extremely close together in a vacuum, not touching, just separated by a tiny gap. To ordinary intuition, nothing much should happen. There is empty space between the plates, empty space outside the plates, and no obvious reason for the plates to move toward one another. Yet quantum physics says the situation is not symmetrical in the way common sense expects. The reason goes back to the electromagnetic field. Even in its vacuum state, the electromagnetic field is not classically silent. It has allowed modes, which are the patterns in which the field can exist and fluctuate. When two conducting plates are brought very close together, they restrict which electromagnetic modes can fit between them. Outside the plates, the field has a broader range of allowed modes. Inside the gap, the possibilities are more limited. That imbalance matters. Because the allowed vacuum structure between the plates differs from the allowed vacuum structure outside them, the energy associated with the field is different in those regions. The result is a measurable force that pushes the plates together. Nothing visible is flowing in. No little springs have been hidden in the apparatus by an overenthusiastic graduate student. The force arises because changing the boundary conditions changes the vacuum behavior of the field. This is the key lesson. The vacuum is not just a name for nothing there. It is a physical state whose properties depend on circumstance. Alter the geometry and the vacuum changes. Alter the permitted field modes, and observable consequences follow. Empty-looking space behaves differently depending on the setup. That is exactly the kind of result one would hope for if the vacuum were real in the physical sense described by quantum field theory. The image of two plates being nudged together by altered vacuum structure is one of the clearest demonstrations that the title is not merely clever wording. Empty space is not full in a vague poetic way. It is full in the sense that the underlying quantum fields remain present, and their allowed states can be modified, producing real effects. The vacuum does not vanish when matter is removed. It continues to participate in physics. It is worth being careful, though, because even here the story can be told in more than one language. The Casimir effect is often described as direct evidence of vacuum fluctuations, and that description is widely used. But the exact interpretation can be framed in mathematically equivalent ways. Some treatments emphasize zero-point energy and vacuum modes. Others emphasize electromagnetic interactions between the materials themselves, described through the same broader formalism. Physicists can debate which picture is more fundamental or more pedagogically helpful. That may sound like a problem, but it really is not. The important point is not that one simple cartoon must be the only approved image. The important point is that all the valid descriptions agree on the observable outcome. Change the boundaries imposed on the field, and the physical behavior changes. The broader lesson survives the interpretive details with impressive confidence. The vacuum is not inert. It responds to conditions, and that response can be measured. The scale of the effect is tiny, which is exactly why precision experimental physics matters so much here. The Casimir force becomes noticeable only when the separation between objects is extremely small, typically on the scale of micrometers or smaller. A micrometer is 1/1000th of a meter, So this is not the sort of thing noticed while rearranging furniture or opening the biscuit tin. It belongs to the world of carefully engineered surfaces, sensitive instruments, and researchers with a heroic tolerance for alignment problems. Over the decades, increasingly refined experiments have measured Casimir forces and related effects with impressive accuracy. Real laboratory work has to deal with all sorts of complications that the idealized picture politely ignores, including surface roughness, temperature effects, material properties, stray electric forces, and the irritating fact that reality rarely arrives pre-flattened and perfectly clean. Yet despite those challenges, the phenomenon has been observed and studied in enough detail to become a standard part of the discussion of vacuum physics. That experimental success matters because it grounds the whole idea. Without such evidence, the vacuum might still sound like an extravagant rebranding of nothingness. With evidence, it becomes much harder to dismiss. Here is a case where empty-looking space exerts influence, where the physical arrangement of a vacuum region changes what happens, and where precision measurements confirm that the theory is not merely decorative. There is also something quietly profound about the style of the effect. The Casimir force does not come from adding a new substance to space. It comes from the fact that the empty region was never just emptiness in the old sense. The plates do not summon matter from nowhere. They alter the allowed behavior of a field that was already there in its vacuum state. That distinction is everything. It keeps the science grounded and prevents the subject from drifting into mystical fog. So the vacuum begins to feel less like a blank and more like a structured background with rules, constraints, and consequences. Empty space is still empty of ordinary stuff in the everyday sense, but it is no longer physically featureless. It has conditions, it has modes, it has measurable behavior under the right circumstances. The Casimir effect is one of the clearest laboratory reminders that the vacuum belongs to nature, not merely to language. And once that is accepted, another possibility becomes harder to ignore. If empty space can produce measurable forces in a controlled laboratory setup, then the vacuum may not only matter between metal plates sitting unglamorously close together in an experiment, it may also influence atoms, radiation, and other parts of physics that seem at first far removed from this narrow gap. The fingerprints of empty space, it turns out, do not stop at the laboratory wall. The vacuum does not only reveal itself in narrow experimental gaps between polished metal surfaces, it also shows up in the behavior of atoms, which is one of the reasons the modern view of empty space became so compelling. Once physicists realized that atomic systems could not be described fully without taking the quantum vacuum seriously, the subject moved from sounding exotic to sounding unavoidable. Empty space was no longer just doing unusual things in special laboratory setups. It was participating in the fine structure of ordinary matter. A good place to begin is with spontaneous emission. This is the process by which an excited atom drops to a lower energy state and emits a photon. At first, that may sound straightforward enough. An electron in the atom has higher energy. Then it loses that energy by releasing light. Simple. Yet the deeper question is what triggers that transition when there is no classical light wave present to disturb the atom. In a purely classical picture, this is awkward. If nothing is externally driving the atom, why should it emit at that particular moment? What starts the process? Quantum electrodynamics provides the answer by treating the atom and the electromagnetic field together as a coupled quantum system. Even when no classical light source is present, the electromagnetic field is still there in its vacuum state. The atom is not sitting in perfect emptiness. It is immersed in the quantum vacuum of the electromagnetic field, and that vacuum can influence the atom's behavior. That is a remarkable shift in perspective. Spontaneous emission is not simply an atom deciding on its own to shine for a while. It reflects the fact that the vacuum is not a blank nothing. The electromagnetic field in its ground state still has quantum structure, and that structure helps make such transitions possible. Apparently empty space is already participating. This is one of the great moments in the story, because it brings the subject down from grand abstractions to the real microscopic machinery of matter. Atoms are not rare cosmic curiosities, They are the ordinary ingredients of the visible world. If the vacuum affects atoms, then vacuum physics is woven into the behaviour of matter all around us, including matter that looks far too solid and sensible to be having conversations with empty space. An even more famous example is the Lamb shift. This effect is named after Willis Lamb, who, together with Robert Rutherford, measured a tiny difference in energy between two atomic states in hydrogen that earlier theory had predicted should be identical. Hydrogen is the simplest atom, which is usually a polite way of saying it becomes the place where physics notices its own mistakes most clearly. When even the simplest atom refuses to follow the expected script, something important is going on. The specific levels involved in the Lamb shift are extremely close in energy, and according to the older Dirac theory they should have matched exactly. But careful measurement showed that they did not. There was a tiny split. Tiny here really does mean tiny, but tiny does not mean unimportant. In precision physics, very small discrepancies are often where reality leaves its most revealing fingerprints. The explanation emerged through quantum electrodynamics, often called QED, the quantum field theory of the electromagnetic interaction. QED became one of the crowning achievements of 20th century physics, and the work of Richard Feynman, Julian Schwinger, and Tsinitiro Tomonaga was central to its development. Their formulations differed in style, but together they helped build the framework that allowed physicists to calculate how charged particles and the electromagnetic field interact with extraordinary precision. Within QED, the electron in a hydrogen atom is not isolated from the vacuum. It interacts with the quantized electromagnetic field, and this interaction slightly shifts the atom's energy levels. The vacuum is therefore not just passive scenery. It enters into the fine details of the atom itself. The Lamb shift became one of the classic confirmations that the vacuum affects measurable properties of matter. This is a powerful result because it changes the status of empty space completely. If the vacuum can shift atomic energy levels, then it is not merely a useful concept for describing rarefied experiments. It is part of the ordinary fabric of physical reality. Every atom exists in the presence of fields. Every charged particle interacts with those fields. The vacuum is not elsewhere. It is built into the behaviour of the world at the smallest scales. There is a nice quiet irony in this. For centuries, emptiness was imagined as what remained when everything interesting had been removed. Modern atomic physics shows almost the reverse. When matter is examined carefully enough, one of the interesting things that turns up is the role of what seemed to be empty space. The vacuum, so often imagined as absence, becomes one of the subtle contributors to the structure of matter itself. This is also where the story begins to feel much broader than a few isolated phenomena. The Casimir effect showed that changing the conditions of empty-looking space can produce measurable forces. Spontaneous emission and the Lamb shift show that the vacuum affects the internal behaviour of atoms. The thread connecting these ideas is clear. Empty space is not an indifferent background. It influences what matter does. That influence is not dramatic in the everyday cinematic sense. Atoms are not bursting into philosophical speeches about the vacuum. The effects are precise, subtle, and best seen through careful theory and sensitive experiment. But subtle does not mean secondary. In physics, very small corrections often reveal very deep truths. The Lamb shift did exactly that. It helped confirm that the quantized electromagnetic field, even in its vacuum state, must be treated as physically real. By now, the phrase empty space is beginning to feel almost mischievous. It remains useful in ordinary language, but it conceals more than it reveals. Space may be empty of visible particles, yet the fields remain. Their vacuum states remain. Their influence on atoms remains. The fine details of spectra, emission and energy levels all carry traces of this deeper picture. And once that much is accepted, another question begins to sharpen. If fields in empty space affect atomic behaviour so deeply, then perhaps they are not merely adjusting the details of matter after the fact. Perhaps they are involved more fundamentally still. Perhaps the fields that fill space do not just influence atoms once particles exist, but help determine what kinds of particles there are, how they behave, and why they possess the properties they do. Because some of the most important features of ordinary matter, including mass itself, turn out to depend on what the vacuum is doing. By this point, empty space has already stopped looking empty in any ordinary sense. Fields fill it. The vacuum is their lowest state, not literal nothingness. That vacuum can influence atoms, shift energy levels, and alter measurable forces. But the story becomes even more striking when one particular field enters the picture, because this field does not merely add small corrections to the behavior of matter. It helps make the existence of familiar matter possible in the form we know it. This is the Higgs field. The Higgs field is one of the most important fields in the standard model of particle physics. Like the other fundamental fields, it is not confined to one region or switched on only in special places. It permeates all of space. That point matters immediately, because it means the field is part of what empty space contains. Even in a region with no atoms, no dust, no gas, and no visible particles passing through, the Higgs field is still there. What makes the Higgs field especially important is that its vacuum state is unusual. For many fields, the vacuum corresponds in a loose sense to the field sitting at zero value, or at least to the simplest available lowest energy condition. The Higgs field does something different. Its lowest energy state corresponds to a non-zero value throughout space. In other words, the vacuum of the universe is not a state in which the Higgs field vanishes. The vacuum includes a persistent Higgs background. That is one of the clearest examples in all of modern physics of why the vacuum is not nothing. Empty space, in this case, carries a physically important background value. The quiet state of the universe already includes structure. The vacuum is not merely active in some subtle abstract sense. It is configured in a way that directly affects the properties of fundamental particles. This idea emerged in the 1960s through the work of several physicists, including Peter Higgs, François Englert, and Robert Brute. Others also made closely related contributions, including Gerald Guralnick, Carl Hagen, and Tom Kibble. The basic problem they were helping to solve concerned the electroweak theory, the framework unifying electromagnetism with the weak nuclear interaction. The theory was powerful, but it required a way for certain force-carrying particles to have mass without destroying the mathematical consistency that made the theory work. The solution was the Higgs mechanism. In broad terms, the Higgs field takes part in spontaneous symmetry breaking, a phrase that will become more important later. For now, the key point is simpler. Because the Higgs field has a non-zero vacuum value, some particles interacting with it behave as though they acquire mass. The W boson and the Z boson, which carry the weak nuclear interaction, gain mass through this mechanism. Without that, the weak interaction would look radically different, and much of the familiar structure of particle physics would not behave as it does. Fundamental fermions, such as electrons and quarks, also gain mass contributions through their interactions with the Higgs field. The details depend on the strength of their coupling to the field. A stronger interaction with the Higgs field corresponds to a larger mass. A weaker interaction corresponds to a smaller one. That does not explain why the coupling strengths take the values they do, which remains one of the deep unanswered questions in particle physics. But it does explain how the field's ever-present background participates in giving particles their masses. This often gets summarized in ways that are partly helpful and partly dangerous. People sometimes say particles move through the Higgs field as though through a kind of molasses, acquiring resistance. That image can be a useful first step, but it is only an analogy, and like most analogies, it begins to wobble if asked to do too much heavy lifting. The real point is not mechanical drag. It is that the vacuum state of the Higgs field is non-zero, and interactions with that background enter the equations in a way that manifests as particle mass. The importance of this became dramatically public in 2012, when experiments at CERN, using the Large Hadron Collider, discovered a new particle consistent with the Higgs boson. The Higgs boson is the quantized excitation of the Higgs field, rather as a photon is an excitation of the electromagnetic field. Its discovery was a major triumph for the Standard Model, and for the decades of work by theorists and experimentalists who had built the framework and the machines capable of testing it. CERN's role here is hard to overstate. The Large Hadron Collider was designed in part to probe exactly this territory, smashing protons together at extremely high energies so that the resulting particle showers could reveal traces of rare processes and short-lived particles. The Higgs boson itself is not the field filling all of space. It is the detectable excitation that confirmed the field's existence. That distinction matters. The field is the persistent background. The boson is a ripple in that background, produced under special conditions and identified through careful analysis. This gives the title a sharper and more tangible meaning. Empty space is full not only because fields are present in their vacuum states, and not only because those vacuum states fluctuate and affect atomic behavior, but because at least one of those fields, the Higgs field, has a background value that helps determine the very properties of familiar matter. The vacuum is not just a stage where physics plays out. It helps set the rules of the performance. At the same time, precision matters here. The Higgs field does not explain all mass in the universe by itself. Much of the mass of ordinary visible matter, especially the mass of protons and neutrons, comes not directly from the Higgs field but from quantum chromodynamics, the theory of quarks and gluons. Inside protons and neutrons, enormous amounts of interaction energy are stored in the strong nuclear interaction. Thanks to the relation between energy and mass and relativity, that interaction energy contributes most of the mass of the matter, making up stars, planets, oceans, teaspoons, and every regrettable flat-pack shelf ever assembled. So the Higgs field is not the whole story of mass, but it is still a profound part of the story. It gives mass to the W and Z bosons and contributes to the masses of fundamental fermions. More importantly for the present question, it shows in a particularly vivid way that the vacuum is structurally important. The empty background of space includes a field with a non-zero vacuum value, and that fact helps shape the universe we live in. This is why the vacuum must no longer be imagined as a passive absence. The Higgs field demonstrates that what appears empty can contain stable background structure, with consequences reaching into the heart of matter. Empty space is not merely where particles happen to be. It is part of why particles have the properties they do. And once one field is seen to have a physically vital vacuum value, it becomes natural to widen the view. The vacuum is not defined by one field alone. Multiple fields, multiple symmetries, and the way those symmetries are realized or broken all help determine what the universe looks like in its quietest state. The vacuum, it turns out, is not just a calm backdrop. It is a highly consequential arrangement of the fundamental fields themselves. The idea of symmetry is one of the quiet organizing principles of physics. A symmetry, in the broadest sense, is a feature of a system that remains unchanged under some transformation. Rotate a perfect circle, and it looks the same. Shift the laws of physics from one place to another, and, as far as anyone can tell, they still behave the same. Run an experiment today or tomorrow, under the same conditions, and the underlying laws are expected to be unchanged. Symmetry, in this sense, is not just visual neatness. It is a statement about what nature treats as equivalent. Physicists love symmetry for good reason. Symmetries help determine what laws are allowed, which quantities are conserved, and how different parts of a theory fit together. But symmetry has a less obvious and far more interesting companion: symmetry breaking. This is what happens when the underlying rules possess a symmetry, yet the actual state of the system does not fully display it. A simple example can help. Imagine balancing a pencil perfectly upright on its tip. In that idealized moment, the setup is symmetric with respect to direction. There is nothing in the laws governing the situation that prefers north over south, east over west, or any other direction. But once the pencil falls, it must choose a direction. The laws did not prefer one direction, yet the final state does. The symmetry of the rules survives, but the symmetry of the actual outcome is broken. That is the general idea. In quantum field theory, a similar thing can happen with the vacuum itself. The equations describing the fields may possess certain symmetries, yet the vacuum state, the lowest energy state those fields settle into, may not reflect the full symmetry of those equations. This is called spontaneous symmetry breaking. The word spontaneous here does not mean random in a careless sense. It means that the underlying laws allow multiple equivalent possibilities, and the system settles into one of them. The vacuum, in other words, is not merely an empty container or neutral silence. It is a chosen state, and that choice can matter enormously. This is one of the deepest reasons the vacuum matters in modern physics. It is not only that fields exist everywhere, or that the vacuum fluctuates, or that atomic levels are shifted by interactions with the electromagnetic field. It is that the vacuum can carry properties that determine what kind of universe is possible. Different vacuum states can lead to different kinds of particle behavior, different force properties, and different forms of order. That is a startling thought when stated plainly. The quietest state of the universe helps decide the rules followed by everything visible. One of the important figures in bringing this way of thinking into particle physics was Yoichiro Nambu. Inspired partly by ideas from condensed matter physics, Nambu showed how spontaneous symmetry breaking could play a central role in the behavior of fundamental fields. His work helped lay the conceptual groundwork for later developments, including the Higgs mechanism and the modern understanding of how vacuum structure shapes particle physics. The key point is that the vacuum is not simply defined by what is absent, it is defined by what state the fields occupy. If the vacuum chooses a configuration that does not preserve the full symmetry of the equations, then the particles and forces emerging from that vacuum can inherit very specific properties. Masses may appear. Interactions may separate into distinct kinds. Certain degrees of freedom may become physically relevant while others remain hidden. The Higgs field provided one especially famous example. The equations of the electroweak theory possess a symmetry, yet the vacuum state of the Higgs field does not preserve that symmetry in the same full way. As a result, the weak interaction and electromagnetism emerge as distinct at low energies, and the W boson and Z boson acquire mass while the photon remains massless. That pattern is not just written into the equations in a simple brute force manner. It depends on the vacuum structure. This is why the vacuum is not an afterthought. It is not the blank paper underneath the writing. It is part of what determines the writing itself. If the vacuum had different properties, then the spectrum of particles, the range of forces, and the architecture of the visible world could be different as well. A different vacuum would not just mean a quieter or louder version of the same universe. It could mean a genuinely different kind of universe. An analogy can help here, provided it is kept on a short leash. Imagine a broad landscape with a high point at the centre and lower ground forming a circular valley around it. The laws describing the landscape are perfectly symmetric with respect to direction. Nothing in the terrain prefers one direction around the circle over another, but if a ball is placed precariously at the centre and allowed to roll, it will come to rest somewhere in the valley. Once it does, the symmetry of the original setup is no longer visible in the actual resting place. The laws remained symmetric. The chosen state did not. That image is often used for the Higgs field, and with good reason, though it is still only an analogy. The main lesson is not the exact shape of some cosmic valley. The main lesson is that the vacuum is a state chosen by the system, and that chosen state can break symmetries in ways that define the world we observe. This raises the significance of empty space to a much higher level. Earlier, the vacuum was shown to influence atomic transitions and small energy shifts. Those were already remarkable results. But symmetry breaking reveals something more profound. The vacuum does not merely tweak the details of the visible world. It helps establish the framework within which those details exist at all. It decides, in part, which patterns are allowed to become real. That is why the vacuum can no longer be imagined as a harmless absence. It has properties. Those properties matter. They can determine which particles exist in stable forms, how forces behave over distance, and what kinds of structures can emerge in the universe. Empty space, if that phrase is still to be used at all, is not a vacant interval between real things. It is one of the real things. This also helps explain why different areas of physics can sound strangely similar when discussing very different systems. Ideas related to symmetry breaking appear in particle physics, condensed matter physics, superconductivity, magnetism, and cosmology. The details differ, often dramatically, but the deeper pattern keeps returning. A system's underlying rules may allow a range of possibilities, and the state it settles into may determine what kind of ordered world emerges. For the question of empty space, that means the vacuum is not just a passive stage waiting for actors. It is closer to part of the hidden script. The visible world depends not only on the laws of the fields, but on the particular vacuum state those fields occupy. Once that is understood, the title becomes even more literal. Empty space is full not just because something is there, but because what is there helps define the entire physical order of the world around us. And there is an even wider consequence. If the vacuum can possess structure and can break symmetries in ways that shape the rules of physics, then there is no guarantee that the vacuum has always been the same. The vacuum of the early universe may not have matched the vacuum seen today. At different temperatures, energies, and cosmic ages, the fields may have settled into different states, which means the story of empty space is not only about what space is now, it may also be about how the universe changed as its vacuum changed with it. If the vacuum helps define the rules of the universe now, then a natural question follows. Was the vacuum always the same? Modern cosmology strongly suggests that the answer is no, or at least not in the simple sense. The early universe was not just a smaller version of the present one. It was vastly hotter, denser, and more energetic. Under those conditions, the fields that fill space may not have occupied the same vacuum states they do today. What counts as the lowest available state can depend on conditions, especially temperature and energy. So the story of empty space may also be part of the story of cosmic history. A useful everyday comparison is a phase change. Water behaves differently as ice, liquid, and vapour, even though the underlying substance remains the same. Temperature changes the stable state of the system. In a loose but helpful sense, something similar may have happened with the fundamental fields of the universe. At extremely high energies in the early cosmos, the vacuum structure may have been different. As the universe expanded and cooled, phase transitions could have occurred, reshaping the vacuum and changing the behaviour of particles and forces. This is one of the most extraordinary implications of modern physics. Empty space is not only a present-day background. Its state may have evolved. The vacuum may have had a history. That idea connects directly to symmetry breaking. At very high temperatures, symmetries that are broken today may once have been effectively restored. As the universe cooled, fields could settle into new vacuum states that no longer preserve the same symmetries. The result would not merely be a cosmetic change, it could alter which particles are massless or massive, which interactions remain unified or separated, and what forms of matter are stable. In the case of the electro-weak interaction, for example, the prevailing picture is that at sufficiently high temperatures in the early universe, the distinction between the electromagnetic interaction and the weak nuclear interaction would not have appeared in the same way it does now. As cooling continued and the Higgs field settled into its non-zero vacuum state, that symmetry was broken in the now familiar pattern. The vacuum changed, and the visible rules of particle physics changed with it. That is a remarkable thought to sit with for a moment. The properties of ordinary matter may depend not only on timeless equations, but on the fact that the universe passed through a sequence of vacuum states as it cooled. The cosmos did not simply contain space. It evolved through different versions of what empty space itself could be. This takes the title to a much larger scale. Empty space is full not only because fields inhabit the vacuum now, but because the vacuum may have guided the development of the universe from its earliest moments. The history of the cosmos may be in part a history of changing vacuum structure. One of the most important theoretical ideas connected to this wider picture is cosmic inflation. Inflation is the proposal that in a very early fraction of cosmic history, the universe underwent an episode of extremely rapid accelerated expansion. The theory was introduced in influential form by Alan Guth in the early 1980s, and later versions were developed by several other physicists including Andre Linde and others working on related inflationary models. The basic attraction of inflation is that it offers explanations for several otherwise puzzling features of the observable universe. It helps explain why the universe looks so geometrically flat on large scales, why widely separated regions of the cosmos have such similar temperatures, and how tiny primordial quantum fluctuations could be stretched into the seeds of galaxies and large-scale cosmic structure. These are serious successes in the broad sense, and inflation remains one of the leading frameworks in early universe cosmology. At the same time, inflation is not a finished story with every detail settled. There are multiple inflationary models. The precise mechanism is not known with certainty. The identity of the field responsible, often called the infleton, remains unclear. Observations of the cosmic microwave background from missions such as NASA's Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck satellite are strongly consistent with inflationary ideas in important ways. But not every theoretical question has been closed. That caution matters. The goal here is not to claim that every version of inflation has been proven beyond dispute. The goal is to show why vacuum physics matters cosmologically. Inflation is one of the clearest examples of a major theory in which a vacuum-like energy state can shape the evolution of the entire universe. In some inflationary pictures, a high-energy vacuum state drives rapid expansion before the fields relax into a lower energy state. In that sense, the vacuum is not merely part of the universe. It can help steer the universe. This also links back to symmetry breaking more generally. As the cosmos cooled, different fields may have undergone transitions that established the particle content seen today. Forces that may once have been more unified became distinct. Particle properties emerged in the context of the vacuum state that won out as the universe evolved. The visible world may therefore reflect not only fundamental laws, but the particular sequence of vacuum changes through which the universe passed. There is something quietly humbling in that picture. The stars, planets, atoms, chemistry, and biology of the later universe may all rest on events in which the vacuum itself changed character. The background was not passive. It participated in cosmic history. By now, empty space has become almost the opposite of what it first seemed. It is not merely the absence left behind after everything else is removed. It is a physical state, a structured state, and perhaps even a changing state. The early universe may have moved through different vacuums the way matter moves through different phases, though in a much deeper and stranger sense. The universe that exists now may depend on which vacuum state became stable as cosmic temperatures fell, and once the vacuum is allowed to shape the history of the universe in that way, another even larger question naturally appears. If empty space can carry energy, influence expansion, and perhaps even drive a primordial burst of accelerated growth, then what does the energy of empty space mean on the larger scales of all? Because when the vacuum is taken seriously in cosmology, it leads directly toward one of the deepest puzzles in all of theoretical physics, the relationship between vacuum energy, cosmic expansion, and the cosmological constant. Once the vacuum is taken seriously in quantum theory and in cosmology, it begins to raise one of the largest and most uncomfortable questions in all of physics. If empty space is not truly empty, and if the vacuum has energy associated with it, then what does that energy do to the universe as a whole? To see why this matters, it helps to return to Albert Einstein. When Einstein developed general relativity, he wrote down equations relating the geometry of space-time to the distribution of matter and energy. At one stage, he introduced an additional term known as the cosmological constant. The reason was partly historical and partly practical. Einstein, like many physicists of his era, assumed the universe was static on the larger scales. His original equations did not naturally support a perfectly static cosmos, so the cosmological constant acted as a kind of balancing term. Later, after Edwin Hubble and others found evidence that the universe is expanding, Einstein reportedly regretted introducing the constant, though the famous phrase about a greatest blunder has acquired a life of its own and may be a little tidier in retelling than history usually is. In any case, for a long time the cosmological constant seemed like an optional extra, an old theoretical patch that no longer appeared necessary. Then the universe became awkward again. In the late 20th century, observations of distant Type 1a supernovae revealed that cosmic expansion is not merely continuing, it is accelerating. The universe is not just growing larger. On the largest observable scales, the rate of expansion is increasing over time. This result emerged through work by major supernova teams and has since been reinforced by multiple lines of evidence. Suddenly the cosmological constant returned, not as a historical curiosity, but as one of the leading ways to describe what the data seem to be saying. Modern cosmology often packages this in the language of dark energy, the name given to whatever is driving the accelerated expansion. The simplest version of dark energy is precisely a cosmological constant, a uniform energy density filling space itself. In other words, the energy of empty space may contribute to the behavior of the entire universe. That is the point where the title stops being merely strange and begins to feel almost outrageous. Empty space is not just full enough to shift atomic levels or produce delicate forces between laboratory plates. If the vacuum carries energy in the right way, it may influence the expansion history of the cosmos itself. The larger structures in the universe may be responding, in part, to the properties of what appears to be nothing. Observationally, this picture has been explored through a broad network of modern cosmology. NASA and ESA have both contributed major missions and datasets relevant to the story. The Planck mission of the European Space Agency mapped the cosmic microwave background with extraordinary precision, helping constrain the large-scale parameters of cosmology. Galaxy surveys and supernova observations have added complementary evidence. More recent projects such as DESI, the Dark Energy Spectroscopic Instrument, continue measuring the distribution of galaxies across vast distances in order to refine the expansion history of the universe and test the nature of dark energy more closely. So on the observational side, there is strong evidence that the universe's expansion is accelerating. On the theoretical side, there is a natural candidate in the form of vacuum energy, or a cosmological constant. That might sound almost too neat, and in a way it is, because when physicists try to estimate the vacuum energy using the machinery of quantum field theory, the answer does not line up with the observed cosmic value in any remotely comfortable way. This mismatch is known as the cosmological constant problem, and it is one of the deepest unsolved tensions in theoretical physics. The basic issue can be stated simply, even though the technical details are formidable. Quantum field theory suggests that quantum fields possess zero-point energies. If one tries in a naive way to add up the contributions from all the modes of these fields, the resulting vacuum energy density comes out absurdly large. Not just a bit too large, not the sort of error that can be solved by a missing factor of 2 or a slightly awkward sign convention. The mismatch is enormous, by far one of the worst disagreements between a theoretical estimate and an observed quantity in all of science. Depending on how the estimate is framed, the discrepancy can run to around 120 orders of magnitude. That is not a normal scientific headache. That is more like discovering that the map, the compass, the road, and the entire concept of direction are having a disagreement. It is hard to overstate how severe the problem is, and yet the observed cosmic acceleration is real, or at least as real as the current evidence strongly indicates. So physicists are left in a peculiar position. The vacuum appears to matter cosmologically, but the most straightforward quantum field theory estimates of vacuum energy do not produce the observed value in any simple or satisfying way. The theory seems to know something important, but not how to say it properly. This is why the cosmological constant problem remains such a serious open question. It is not merely a loose end in one corner of theoretical physics. It sits at the intersection of quantum field theory, gravity, and cosmology. It suggests that there is something still incomplete in the way these frameworks fit together. The vacuum is clearly not irrelevant, yet the connection between vacuum energy and cosmic expansion remains deeply mysterious. That mystery changes the scale of the whole discussion. Earlier, empty space influenced laboratory effects and atomic structure. Those results were already enough to prove that the vacuum is physically real in a meaningful sense. But now the issue reaches the full size of the observable universe. If empty space carries energy, then the properties of the vacuum may shape not just local experiments, but the fate of cosmic expansion itself. This is one of the reasons the subject feels so profound. The old intuition treated emptiness as what remained when all the interesting content had been removed. Modern physics arrives at almost the reverse. Empty space may carry fields, fluctuations, background values, and perhaps even a form of energy that steers the evolution of the cosmos. The more carefully the vacuum is examined, the less it resembles nothing. And once empty space becomes this consequential, the question naturally broadens beyond physics into philosophy as well. If the vacuum is a physical state, if it has structure, energy, and consequences, then what exactly is meant by nothing anymore? Can that word still do the work people often want it to do? Or has modern physics made literal nothingness retreat so far beyond the reach of actual science that what people call nothing is almost always some kind of something after all? At this point, one small word has become suspiciously overloaded. Nothing. It sounds simple, perhaps the simplest word in the language. A child understands it. A philosopher distrusts it. A physicist, if cornered at a public lecture, usually discovers that it means at least 3 different things before the first cup of tea has gone cold. And much of the confusion surrounding empty space comes from allowing those meanings to blur together. In ordinary speech, nothing often means nothing noticeable, nothing in the cupboard, nothing on the road, nothing happening. This is a practical, human-sized use of the word, and it works perfectly well for everyday life. But physics is not dealing in practical impressions. Physics asks what is physically present, what laws apply, what states are allowed, and what measurable effects follow. Once those questions are asked, nothing becomes much harder to define. The first distinction that matters is the difference between philosophical nothingness and the physical vacuum. Philosophical nothingness is the idea of absolute non-existence. No matter, no radiation, no fields, no space-time, no laws, no structure, no geometry, no background conditions, no possibilities waiting quietly in reserve. Not emptiness within a world, but the total absence of any world at all. That is a very strong idea. It is also not what physicists mean when they talk about the vacuum. The vacuum of quantum field theory is already a richly structured physical state. It contains fields. It contains a lawful framework. It contains allowed states, correlations, and quantum properties. It may carry vacuum expectation values, as in the case of the Higgs field. It may contribute to measurable effects such as the Casimir effect, spontaneous emission, and the Lamb shift. It may even connect to cosmic expansion through dark energy or the cosmological constant. Whatever else the vacuum may be, it is not absolute non-existence. That distinction is absolutely essential, because without it the whole discussion begins to slide. When quantum physics says empty space is full, it is saying something technical and physical. It is not claiming that literal nothingness somehow turns out to be secretly crowded. It is saying that what looks empty in the everyday sense is, at the level of modern physics, a vacuum state of real fields and real laws. The word empty is being corrected, not the word logic. This is why popular statements about the universe coming from nothing often need very careful handling. They can be useful headlines, and they certainly have a knack for attracting attention, which, to be fair, is a survival skill in modern publishing. But the version of a nothing used in those discussions is often not literal nothingness. It is usually some sort of quantum vacuum, or a lawful background, or a dynamical space-time setting, or a state governed by equations that already exist. In other words, it is not nothing in the absolute philosophical sense. It is a physical setup with very non-zero amounts of structure. This does not make such discussions worthless. Far from it. They can point toward fascinating questions about cosmology, quantum gravity, and the deep origin of physical law, but they do require conceptual honesty. If one begins with a quantum vacuum, one has not begun with nothing. One has begun with a particular kind of something, even if it is much thinner, stranger, and more abstract than matter, planets, or stars. Lawrence Krauss became one of the best-known public figures associated with this style of discussion, especially through arguments about how the universe might arise from nothing. His work helped bring these questions to a large audience, which is no small achievement. But it also illustrated how easily definitions can blur in public conversation. Much of the disagreement around such claims has not been about the mathematics alone. It has been about what the word nothing is being asked to mean. If one person means a quantum vacuum and another means absolute non-existence, they are not disagreeing within the same conceptual room. They are standing in different buildings shouting through the windows. That is why precision matters here. A vacuum state is not philosophical nothingness. A dynamical space-time is not philosophical nothingness. A lawful quantum system with allowed fluctuations is not philosophical nothingness. These may be very sparse states compared with the ordinary material world, and they may be astonishingly unlike common sense, but they are still physically rich conditions. They are describable. They are structured. They belong to science because they have properties that can, in principle or in practice, enter physical explanation. There is also a deeper reason to keep these definitions clean. Without that care, the real achievement of modern physics gets obscured. The remarkable discovery is not that science has triumphantly converted absolute nothing into something. The remarkable discovery is that what people once assumed was simple emptiness turns out to be physically complex. The vacuum is not a trivial absence. It is one of the most sophisticated ideas in theoretical physics. That matters because this whole journey depends on conceptual discipline. The argument so far has built from laboratory vacuums to relativity, from quantum uncertainty to fields, from zero-point energy to vacuum fluctuations, from atomic behavior to the Higgs field, and from symmetry breaking to cosmology. All of that rests on the physical meaning of the vacuum. If that physical meaning is casually swapped with philosophical nothingness, the argument becomes foggy just when it ought to be sharpest. So it helps to state the core point plainly. Quantum physics says empty space is full in a technical physical sense. It says that regions with no ordinary matter are still occupied by fields, governed by laws, structured by vacuum states, and capable of influencing measurable phenomena. That is already astonishing enough. There is no need to exaggerate it into a claim about literal non-being secretly doing science. There is perhaps something slightly amusing in the fact that the deeper physics goes, the less useful ordinary language becomes. Empty does not quite mean empty. Nothing does not quite mean nothing. Quiet does not quite mean still. Space does not quite mean a blank container. Yet this is not wordplay for its own sake. It reflects a genuine mismatch between human intuition, which evolved for handling fruit, weather, and social embarrassment, and the structure of reality at fundamental scales. Once that is accepted, the question becomes sharper again. If the vacuum is physically real, if it is a genuine state rather than a mere absence, then it becomes sensible to ask more of it. Is the vacuum stable? Is it unique? Is the quietest possible state of the fields truly final? Or could there be other possible vacuum states, deeper ones, stranger ones, or ones that belong to different physical conditions? If empty space is a state the universe occupies, then perhaps it is not the only state available. and that raises one of the most unsettling and fascinating possibilities in modern theoretical physics. The vacuum itself may not be permanent. Once the vacuum is understood as a real physical state, an unsettling possibility appears almost automatically. A physical state can be described. It can have properties. It can influence particles and forces. But it can also raise another question, one that sounds simple and turns out not to be. Is it truly the lowest possible state, or only the lowest state available under present conditions? This is where the idea of a false vacuum enters the story. A false vacuum is a metastable state. That means it can look stable, behave stably, and persist for an extremely long time, while still not being the absolute lowest energy state that is in principle possible. It is a local minimum rather than the deepest minimum overall. The system is settled, but not settled as completely as it could be. A useful comparison is a ball resting in a shallow valley, while a deeper valley exists elsewhere beyond a hill. The ball can remain where it is for a very long time. It is not rolling about chaotically. It is stable in the everyday sense. But it is not in the lowest possible location. It is only locally stable. If some process allows it to cross the barrier, it can move into the deeper valley. That, in broad outline, is what metastability means. In field theory, the vacuum can be like that. The fields may occupy a state that is stable for all practical purposes over enormous timescales, yet still not represent the absolute lowest energy configuration available in the full structure of the theory. That is what physicists mean by a false vacuum. The word false does not mean imaginary or mistaken. It means deceptively final. It looks like the vacuum, acts like the vacuum, and may indeed function as the vacuum for the entire visible universe, yet it may not be the deepest vacuum possible. This idea matters because once the vacuum is treated as a physical state, questions of stability become unavoidable. It is no longer enough to ask what the vacuum does. One must also ask whether the vacuum is unique, whether it is permanent, and whether alternative configurations are possible. In a way, this is a mark of scientific maturity in the subject. The vacuum has stopped being a vague absence and become something real enough to worry about properly. The reason the idea attracts attention is that it reveals how deep the notion of vacuum has become. If the vacuum were merely empty space in the old common sense, there would be no meaningful question of decay. Empty is empty, and that would be the end of it. But once the vacuum is understood as a field configuration, a ground state, or perhaps only a metastable state, then transitions between different vacua become part of the subject. The vacuum becomes something with a kind of internal landscape. This issue appears in modern discussions of the Standard Model, especially in relation to the Higgs field. Calculations using the measured masses of the Higgs boson and the top quark suggest that the electroweak vacuum may sit in an interesting region of parameter space, depending on the precise values of these and other inputs, and depending on how one extrapolates the Standard Model to extremely high energies. The present vacuum may be stable, metastable, or in a finely balanced region close to the border between the two. That sentence carries an important warning label. These conclusions are model-dependent and scientifically nuanced. They depend on precision measurements, on renormalization group running, on assumptions about physics at very high energies, and on whether the Standard Model remains valid all the way up to scales approaching quantum gravity. So this is not an area where sweeping declarations are wise. The evidence does not entitle anyone to say, with full certainty, that the vacuum is metastable in a final closed sense. What can be said is that modern calculations make the question meaningful and non-trivial. This is one of those places where physics becomes both more precise and more humbling at the same time. They also appear as serious ingredients in attempts to describe how the early universe may have evolved. What matters most for the present question is the broader lesson. The vacuum is not just a setting. It has an energy structure. It may admit multiple configurations. It may be stable, metastable, or unstable depending on the theory and the regime. Once physics began treating empty space as a real state, it opened the door to all the questions one normally asks of real states. Is this the lowest one? Is it permanent? Can it change? Could another one exist? That is why the subject feels increasingly far removed from the old image of emptiness as blank absence. The vacuum now has topology, transitions, structure, and possible alternatives. It behaves less like a hole in reality, and more like one of reality's deepest ingredients. Even its apparent quiet may conceal an unfinished question. And that question does not stop with cosmology or particle physics. The vacuum also sits at the centre of one of the greatest unresolved tasks in science. Quantum field theory describes fields in a background space-time with extraordinary success. General relativity describes space-time itself as dynamical geometry, with equal brilliance on large scales. But when these two frameworks are pushed toward one another, especially in the deepest questions about empty space, the fit becomes uneasy. Which means the vacuum is not only a topic in the story of particles and the early universe, it is also one of the places where physics begins to run out of agreed answers. By the time empty space reaches the edge of quantum gravity, the question has become so deep that modern physics no longer offers a fully agreed answer. That is not because the subject is vague, and it is not because physicists have been too busy naming particles after household pets. It is because two of the greatest theories ever built describe the world brilliantly in their own domains, yet resist being joined into one final picture when the deepest structure of space itself is at stake. Those two theories are quantum field theory and general relativity. Quantum field theory describes the behavior of particles and fields at very small scales with astonishing accuracy. General relativity describes gravity, space-time, black holes, and the large-scale structure of the universe with equal brilliance in its own domain. Each theory works extraordinarily well. The trouble begins when they are pushed toward the same question. Quantum field theory usually assumes a space-time background. Fields exist on that background. They fluctuate, interact, and produce the particles and forces described by the standard model. The geometry of space-time may be simple or curved in some treatments, but in the basic structure of the theory, there is still a stage on which the drama unfolds. The fields are quantized. The background is usually treated more classically. General relativity takes a different view. In Einstein's theory, space-time is not a passive stage. It is dynamical. It bends, stretches, ripples, and responds to matter and energy. Gravity is not a force acting within space-time in the ordinary sense. Gravity is the geometry of space-time itself. That means the thing quantum field theory often takes as a background is, in general relativity, one of the central physical actors. This is the tension. One theory quantizes the actors while usually keeping the stage in place. The other theory tells us the stage is itself part of the physical story. And when the stage is no longer fixed, the whole question of what empty space really is becomes far harder. This is where quantum gravity enters the story. Quantum gravity is the unfinished search to reconcile quantum theory with gravity in a fully consistent way. It is the attempt to understand what space-time is when both quantum principles and gravitational geometry must be taken seriously at once. It is also one of the clearest signs that the title of this video eventually opens onto one of the biggest unanswered questions in science. If empty space is full, then what is space itself at the deepest level? Is it continuous, emergent, quantized, geometric, something even stranger? At present, no final accepted theory answers those questions in a way the whole field agrees on. That must be said plainly. There is no settled framework that has replaced both general relativity and quantum field theory in the deepest regime and been confirmed by decisive experiment. There are powerful approaches, rich mathematical programs, and serious research traditions, but no final winner. One major approach is string theory. In string, another major approach is loop quantum gravity, associated with figures such as Carlo Rovelli, Lee Smolin, and others. Loop quantum gravity begins from a different instinct. Rather than starting with strings in a higher dimensional setting, it tries to quantize spacetime geometry itself more directly. In this approach, space may have a discrete or granular structure at extremely small scales, with areas and volumes taking quantized values in some formulations. The old idea of space as a smooth continuum may then be only an approximation valid at larger scales. These two programs differ greatly in style, mathematics, and physical intuition, and neither should be presented as a settled answer. They are approaches, not conclusions. They show that serious physics has reached the point where empty space can no longer be treated as a self-evident blank. The vacuum may sit on top of a deeper structure that current theory has only partially grasped. There are other approaches too, including asymptotic safety, associated with ideas developed by Steven Weinberg and others, in which gravity may remain well defined at high energies through a particular kind of mathematical behavior. There are also approaches involving emergent spacetime, holography, causal sets, and more. The details vary, but the shared lesson is unmistakable. Once gravity and quantum theory are both taken seriously, empty space becomes one of the deepest mysteries in all of science. This matters because the vacuum in ordinary quantum field theory may not be the final word. If spacetime itself is quantum in some deeper sense, then what appears to be the vacuum may rest on a more fundamental layer of reality. The fields might not simply inhabit space in the way current theory describes. Space itself might emerge from more basic quantum relations, algebraic structures, or geometric building blocks that do not resemble everyday emptiness at all. At that point, even the word vacuum begins to feel provisional. It remains useful and it remains physically powerful within existing theory. But it may not be the last concept in the chain. There may be a deeper account still waiting, one in which empty space is not only full of fields, but also built from structures not yet fully understood. That is what makes this frontier so compelling. The question began with a common-sense image of emptiness as simple absence. It led through relativity, quantum fields, zero-point energy, atomic effects, the Higgs field, symmetry breaking, cosmology, and vacuum stability. And at the far edge of all that, the idea of empty space runs into the boundary of current knowledge. Physics can say a great deal, but not everything. The deepest structure of the vacuum remains unfinished territory. Yet there is a useful kind of calm in that uncertainty. The absence of a final answer does not erase what is already known. Quantum field theory and general relativity both remain extraordinarily successful where they apply. The vacuum is physically real within those frameworks in powerful and measurable ways. The remaining question is not whether empty space matters, it is how deep that mattering goes. And from this speculative edge, it helps to return for a moment to firmer ground. However strange the vacuum may be in the deepest theory, and however incomplete the union of quantum theory with gravity remains, there is still a practical question waiting quietly in the background. If empty space is so full of structure, fields, and quantum behavior, why does the everyday world look so calm, solid, and ordinary most of the time? After all of this, a very sensible human question tends to appear. If empty space is full of fields, fluctuations, background values, and quantum structure, then why does the world not look completely bizarre all the time? Why do walls remain wall-like, tables remain obediently table-shaped, and bedrooms at midnight fail to glow with obvious exotic vacuum drama? Why does ordinary life look so calm if the underlying physics is so restless? The short answer is that the large-scale world emerges from the quantum world in stable, ordered ways. The deeper reality may be quantum, but the reality most human beings encounter is the macroscopic outcome of an enormous number of interactions averaging, stabilizing, and suppressing the more delicate quantum features that would otherwise stand out. One of the most important concepts in this story is decoherence. Decoherence is the process by which quantum systems lose the kind of coherent behavior that allows for delicate superpositions and interference effects to remain visible. The word sounds technical, but the idea is manageable. A small quantum system can, under the right conditions, preserve subtle phase relationships that make distinctly quantum behavior possible. But in practice, most systems do not remain isolated. They interact with their surroundings constantly. They interact with air molecules, thermal radiation, nearby matter, electromagnetic environments, and countless other degrees of freedom. Those interactions rapidly spread information about the system into the wider environment. When that happens, the coherent quantum relationships that would allow obvious interference between different possibilities become extraordinarily hard to maintain. The system begins to behave, for practical purposes, more classically. This is often called environment-induced decoherence, because the environment is what drives the process. The world is full of interactions, and those interactions are exceptionally efficient at erasing the clean visibility of fragile quantum effects at large scales. That does not mean quantum mechanics stops applying. It means the conditions required for visible quantum weirdness become harder and harder to preserve as systems become larger, warmer, and more entangled with their surroundings. A carefully isolated electron or photon can display striking interference behavior in the laboratory. A chair, by contrast, is made of an absurd number of particles interacting with one another and with the environment at every moment. A chair is not a large electron. It is a deeply entangled, thermally noisy, environmentally coupled object. It decoheres with astonishing speed. This helps answer the concern directly. The vacuum being full does not mean empty rooms should visibly shimmer with strange field excitations in any everyday sense. The underlying fields are real, their vacuum states are real, their effects are real. But the macroscopic world emerges through stable patterns that suppress the obvious appearance of microscopic quantum behavior. What human beings experience most of the time is not raw quantum delicacy. It is the large-scale, decohered, effectively classical result. There is a useful analogy here, though only up to a point. Imagine looking at the surface of the sea from very high above. From a great distance, the ocean may appear smooth and continuous, yet close inspection reveals waves, turbulence, foam, currents, and countless local irregularities. The large-scale calm was never a denial of the finer structure. It was the large-scale appearance that emerged when details were averaged over. In a similar way, the classical world is not proof that the quantum vacuum is absent. It is the stable, large-scale face of a deeper physical reality. Modern quantum foundations research has explored this question in great detail. Decoherence is now a central part of the way physicists understand the transition from quantum possibilities to classical appearance, even though interpretive debates still remain about what exactly decoherence does and does not solve. It explains extremely well why interference becomes unobservable in ordinary macroscopic settings. It explains why certain states become robust and effectively classical. What it does not do, by itself, is settle every philosophical question about measurement or the ultimate interpretation of the wave function. Those debates continue, and wisely so because nature has not made them trivial. But for the present purpose, decoherence already does enough. It shows why the world can rest on quantum fields and vacuum structure without looking like a surreal light show. It explains why ordinary matter behaves in stable, predictable ways, even though its underlying description involves fields, probabilities, and vacuum states. It brings the discussion back to human scale without undoing any of the deeper science. This matters because otherwise the title might begin to sound detached from everyday life, as though the quantum vacuum belongs only to particle accelerators, dense equations, and people who enjoy discussing renormalization before lunch. In reality, the reason the everyday world looks ordinary is not that the vacuum is irrelevant. It is that ordinary life is the large-scale outcome of deeper processes that have settled into remarkably robust forms. A wooden table does not need to announce the Higgs field in order to depend on it. A glowing atom does not need to mention quantum electrodynamics in order to be shaped by it. A room does not need to visibly fizz with vacuum fluctuations in order for the fields of quantum theory to be present. The world can be deeply quantum without being theatrically quantum. This is also why classical language remains so useful. Newtonian mechanics still works beautifully for falling objects, orbiting planets in many contexts, bridges, engines, and billiard balls, despite the fact that the deeper reality is not Newtonian in the fundamental sense. Classical physics emerges as an approximation, and often an astonishingly accurate one, when the details of quantum coherence become negligible at the scales involved. Smoothness, solidity, and predictability are not illusions. They are real large-scale patterns. They are simply not the deepest level of description. There is something quietly reassuring in that. The universe does not require human beings to experience every layer of reality all at once. Most of the time, the world presents its classical face. It gives rocks, rain, doors, books, oceans, and teaspoons. Beneath that face lies a deeper description involving fields, vacuum states, and quantum structure. But those deeper layers do not usually erupt into ordinary perception, because the macroscopic world is stabilized through decoherence, thermodynamics, and the behavior of huge collections of interacting particles. So the calm appearance of the world is not a contradiction of the restless vacuum. It is what a restless vacuum looks like when filtered through large numbers, stable structures, and constant environmental interaction. The full quantum world is still there, but it is not displayed in its most delicate form at human scale. That brings the story back into focus. Empty space can be full without making life visibly absurd. The vacuum can be structured without turning every quiet room into a special effect. The deeper reality can remain strange while the familiar world remains solid. Those two things are not rivals. They are levels of the same world. And with that in place, the different meanings of full can finally be gathered together. Because by now the word has accumulated quite a lot of work. Empty space is full of fields. It is full of vacuum structure. It is full of possible fluctuations. It is full of background values such as that of the Higgs field. It may be full of energy relevant to cosmology. And yet it also remains, in ordinary life, empty enough to look calm. All of those meanings can now be brought into one coherent picture. By now, the title can be answered plainly. Quantum physics says empty space is full because empty space is not the absence of physics. It is the presence of fields in their vacuum states. It is the lowest energy condition of a real physical system, not the disappearance of the system altogether. What once looked like a blank gap in the universe has become, through modern physics, a structured state with measurable consequences. That change in understanding unfolded gradually. Classical thought first treated emptiness as a philosophical problem, then as an experimental possibility. Relativity changed the picture by showing that space and time form space-time, and that even a region without matter can still possess geometry, curvature, and gravitational structure. Space stopped being a silent stage and became something physically meaningful in its own right. Quantum mechanics then pushed much further. At small scales, nature does not behave like smooth classical machinery. Systems cannot in general be reduced to perfect stillness in the old sense. The uncertainty principle and the broader architecture of quantum theory mean that the lowest state of a system is not always a featureless rest. That insight opened the door to a new view of the vacuum. Quantum field theory completed the transformation. In that framework, the basic ingredients of reality are not tiny isolated beads moving through a void, but fields extending throughout space. The electron field, quark fields, photon field, gluon field, Higgs field, and others remain present whether or not visible particles are passing by. What people call particles are excitations of those fields. So a region with no particles is not a region with no physical content. The fields remain, their vacuum states remain. Empty space is already occupied in that deeper sense. From there, the meaning of full becomes more precise. Space is full, first, in the sense that fields are present everywhere. Second, it is full in the sense that the vacuum is a real ground state, not literal nothingness. Third, it is full in the sense that this ground state is not classically silent. 0-point energy and quantum fluctuations mean the vacuum retains irreducible structure even in its quietest allowed condition. Those are not just abstract statements. The Casimir effect showed that changing the boundary conditions of empty-looking space can produce measurable forces. The Lamb shift and spontaneous emission showed that the electromagnetic vacuum influences atomic behavior. Quantum electrodynamics made it clear that empty space participates in the fine details of matter. The Higgs field made the story even more vivid, because its non-zero vacuum value helps determine the properties of fundamental particles. The vacuum is not merely active, it is structurally important. Then the scale widened again. Symmetry breaking showed that the vacuum need not mirror the full symmetry of the equations, and that this matters for which particles exist and how forces behave. Cosmology extended the idea further still. In the early universe, vacuum states may have changed as the cosmos cooled. Cosmic inflation introduced the possibility that a vacuum-like energy state helps shape the expansion of the young universe. The cosmological constant problem raised the astonishing possibility that vacuum energy may be tied to the accelerated expansion of the universe today, even though the theoretical and observed values still refuse to align in a satisfying way. So when modern physics says empty space is full, it does not mean one simple thing. It means several connected things at once. It means fields exist everywhere. It means the vacuum is a physical state. It means that state has structure and consequences. It means some fields have non-zero background values. It means vacuum properties may influence the history and expansion of the universe. And it means that what appears empty to human intuition is, under deeper inspection, one of the richest concepts in all of science. That is why the title is not a poetic trick. It is a compressed statement of a real scientific revolution. Earlier ages imagined emptiness as what remained when everything else had been removed. Modern physics discovered that removal does not lead to a blank. It leads to fields, vacuum structure, fluctuations, symmetry breaking, and perhaps even clues to the deepest unfinished theory of space itself. And yet none of this means that the everyday world becomes unreal or absurd. The familiar classical world still emerges in stable ways, which is why rooms look calm, tables stay solid, and ordinary life does not resemble a permanently malfunctioning particle detector. The vacuum can be full without becoming visually theatrical. Reality can be deeply strange without becoming unlivable. Which leaves one final thought hanging quietly in the background. The most apparently empty parts of the universe are not places where law has run out or where reality has faded to nothing. They are places where the hidden structure of physics becomes hardest to ignore. The silence was never truly empty. It was only deeper than it first appeared. So the old image of emptiness, a bare absence, a clean gap, a perfect nothing, has not survived contact with modern physics. In its place stands a quieter and far more intricate picture. Space can be structured, dynamical, and physically consequential even when no matter is visible. What looks empty can still contain fields, vacuum states, background values, and the subtle conditions that help shape the behavior of matter and the history of the cosmos. That is the real meaning of the title. Quantum physics does not say empty space is full as a casual metaphor or a clever bit of wording. It says it because the vacuum is the lowest state of real fields that permeate the universe. From the early debates of Democritus and Aristotle, through relativity and space-time, through quantum mechanics, quantum field theory, the Casimir effect, the Lamb shift, the Higgs field, and out into cosmology, the same lesson kept returning in deeper forms. Emptiness was never as simple as it looked. Some parts of that story now stand on extraordinarily firm ground. Quantum fields, atomic vacuum effects, and the role of the Higgs field belong to highly successful modern physics. Other parts remain unfinished, including vacuum energy, cosmic inflation, and the final union of quantum theory with gravity. That uncertainty is not a weakness in the story. It is part of its honesty. Modern physics did not merely discover hidden objects floating inside empty space. It discovered something stranger and more profound. Empty space was never as empty as human intuition first imagined.